All right, so today we're going to take a look at section 4.3, which is titled Riemann sums and definite integrals. If you've printed things out, you're going to be very grateful today that you've got a printout because there's a lot of writing. If you didn't print things out, maybe you just like and prefer to write them down in your notebook, you're probably not going to have ample enough time to fill those in as we go today, and you're going to need to go back and fill them in later because I don't want to hold up everybody just for the writing portion of it. So we're going to take a look first at what a Riemann sum is. So let f be defined on a closed interval from a to b. So that means there's no holes or asymptotes. It's defined. And let delta be a partition of ab, just like we saw last time, where we've divided it up into intervals. Okay? Those intervals have locations from x0, which is the endpoint a, all the way to xn, wherever we choose to end with it at the endpoint b. So like on your quiz today, I think did I give you 4 intervals? That's what I usually do, 4 intervals. And so it'd be from x0 to x4. Those are the numbers. Where delta x sub I is the width of the ith subinterval. If c sub I is any point in the ith subinterval, then the sum from I equal 1 to n of f of c sub I delta x from x sub I minus 1 is less than or equal to c sub I is less than or equal to x sub I is called the Riemann sum of f for the partition delta. The sums we saw in our last section are examples of Riemann sums, but there are more general Riemann sums than those covered. So in particular, what happened in section 4.2 is we looked at using the left-hand endpoint, the right-hand endpoint, and the midpoint. Those are the 3 locations that we looked at. What this is telling you is it doesn't matter what point you use, the left endpoint, the right endpoint, the midpoint, or any other point at all, we can still find this thing called the Riemann sum. And if we take things as limits go to infinity, it will be exactly the same, whether we take the left endpoint, the right endpoint, or any point in between. All right? That's what the c sub I is saying, is it doesn't really matter which of those points it is or anything else, it will work. So the definite integral, f is defined on the closed interval ab, and the limit of the Riemann sums over the partitions, and I told you the delta is going to go to 0. That's equivalent to letting your rectangles become infinitely, or having infinitely many rectangles, right? So having infinitely many rectangles or having the width of the rectangles become infinitely small. Those are equivalent definitions. What happens is if we let those rectangles get infinitely small, that approaches something that we've already seen in section 4.1. In particular, it is the integral over f of x dx. But now what you see is you see numbers at the top and the bottom. That's why this is called a definite integral, is because it's defined specifically between a and b. So in particular, what those antiderivatives find for you, that we saw in section 4.1, is they find the area under the curve. Right? Derivatives found slopes of tangent lines for us. That's what they really are, right? The concrete visual picture that you should have when you're finding a derivative at the point is it's the slope of the curve, or the slope of the tangent line at that point. What we're finding when we've got our limit going from a to b, right, our definite integral values, is we're finding area. Now, it's a little trickier than just area, because what happens if the graph is not completely above the curve? What if it crosses the curve and so forth like that? But for talking about it being above the curve, it is literally finding the area from A to B. Okay? Let's see, what else did I maybe not say? A is lower limit, B is the upper limit. I think I'm good. So when we're taking a look at continuity, we did this for derivatives as well. When we have something that's continuous, it is automatically integrable. Now, we can do some things that are not continuous and find their integrations as well. So it's not limited to those functions. But if we know we have something that's continuous, so think about polynomials, right? Think about radicals. Radical functions. Think about rational functions where we don't overlap, like, the asymptotes. All of those functions, we're going to be able to do this for automatically. And we're going to get some additional pieces as well. So this integral from a to b of f of x dx will always exist for continuous functions. And this is the one that I was talking about before, all written out for you. If f is continuous and non-negative, that means it's above the x-axis, then what we get when we're finding this definite integral from a to b is actually the exact area. It's not an approximation like we did in 4.2, right? It's actually going to be the exact area. Now we're going to take a look both in this section at what happens when we find this exact area as it's described, and also what happens if we were looking at these from a geometric perspective. So that's where we're headed next. All right, this is actually on page 277. It's problem number 16, and the function itself is given to you as a graph. I should probably go back and edit these slides so I can put it in there now that there are greater capacities inside of this area to do this. But the graph looks like this. It is, let's use red. It has this drop down. Whoa, let's use a line. That'd be better. This drop down like this. And work. And it's shaded in. And that's what the graph looks like if we look at this as it's given to us on that page. It's shaded in, it looks something like this. Okay? And the graph's equation is also given to us. It tells us on that page that the function that this is dealing with, f of x, is just the function x squared. And it says it wants us to set up this interval. Okay, sorry, there we go. So this is the graph of 2. Okay, so this is actually what the picture starts out looking like when you're looking at one of these problems. All these details are all in place. And the question asks us to set up the definite integral. It doesn't ask us to find it. It just asks us to figure out what the notation should look like. Okay, so the notation should look like an integral symbol. The upper and the lower limits are where it starts and it ends on the shading. So where is it starting on the shading? X values is what we're looking at. 0. And where will it end? At 2. So reading the graph from left to right, it starts at 0, it ends at 2. And what's the equation that we're given? X squared. And we talked about in section 4.1 that the integral symbol, that script S, is like the beginning marking of like a parenthesis. And the ending marking is always going to be for us dx or d whatever the variable is. And so ours is going to be dx here because our variable is x. So it's almost like you're starting with a parenthesis and you're ending with a parenthesis with these sort of bookends. This is all the question's asking you to do. Okay, it's not asking you to solve it. It's just asking you to set it up. Okay, the work inside of this section is a lot of the precursor to what we're going to do in 4.4, which is going to be to solve this type of an equation or expression. Okay, easy enough? No problem? Okay. The next ones we're going to take a look at ask us to sketch the region. So we're actually going to draw the sketch. Grab your calculator if you wish on some of these if you're not quite sure you're getting it right or the crossing points. This one's not one you probably need a calculator for, but some of them might be in this section. And it's asking us specifically to use a geometric formula. Okay? So if it's asking for that, it's telling you that the shape itself is going to be something that you should recognize from geometry. All right? So we're going to take a look at the first one. The first one is the equation y equal 4. That's what this means right here, is the equation is y equal 4. What does the equation y equal 4 look like? A line, but what kind of line? Horizontal line at a height of 4. So this is a horizontal line at a height of 4. So it looks something like this. I'll draw it in red. Let's make it a thicker red since I changed that a minute ago. Wow, that was not what I was expecting. Let's try again. Something in between. How about that? Okay, 4. And it tells us how far to go. It says to start at x equals 0. That's the y-axis. And it tells us to go out to x equals 3. So that's here. So the graph itself will start and end at those locations. And if I'm shading from 0 to 3 under the graph of this y equal 4, I get this shape. Okay, everybody good so far? You know this shape. You do not need calculus to find the area of this shape. That's why they're putting it in this particular section, okay? So when you get to a quiz on this material and when you get to the test on this material, there are going to be at least one question in those areas where I ask you specifically to use this. Use geometric formulas. And if you don't use geometric formulas and you use calculus, you didn't do what the question asked. So pay attention to the directions of the question when you're encountering those in different situations. What is the shape? It's a rectangle. How do you find the area of a rectangle? Length times width, or base times height if you prefer. What are the length and the width, I don't care what order they're in, of this shape? 4 and 3. And 4 times 3 is 12. Okay, so we're pulling this back into something that we know back in geometry. That's what we're really doing. And not even geometry, high school geometry. This is like middle school geometry stuff, right? Maybe even elementary, upper elementary when you first encounter some of these formulas. So this is not stuff that's going to be unfamiliar to you. Now, when you take a look at the next one, the shape's a little bit more difficult. It's not quite as straightforward. It's not a rectangle, in other words. So you know what this graph looks like, though. What is this a graph of? A line. What's the y-intercept of the line? 4. So we've got a y-intercept at 4. And a slope of 3. And how far out am I supposed to be going? 2. This is going to x equal to 2. So you can actually just, rise and run it over if you wish. So I'm going to up 2 and over 1, rise over run. And then I'm going to up 2 again and over 1. Puts me right here, if I've drawn it well, which I'm not promising I have. But it's basically like this shape. Okay, did I get it okay? Oh, it was 3. Sorry. 3. Up 3 and over 1. Oh my goodness. Let's fix that. Up 3 and over 1. Try again. Okay, how's that? Is that better? I think that's better. Okay, all good? Okay, so I'm going to shade from the 0 to the 2 because my limits go from 0 to 2. So if you want to think about dropping down a perpendicular line to the x-axis, right, that would be a helpful way to draw it. And then you're shading this in. Okay, so without me asking you what the formula is, do you know what the shape is? It's a trapezoid. You may want to use a trapezoid formula if you remember it, and if you don't, there's another way to do the problem. So one way to do this is as a trapezoid. Any other thoughts of how I could do this? Yes, you could change it into a triangle and a rectangle or a square depending on the shape of the bottom piece. So you could break it apart right here and make the bottom part this rectangle, right? And the top part a triangle. And that would be an acceptable way of doing it too. Let me do it as a trapezoid and then we'll do the triangle-rectangle combination if you prefer that, because it doesn't make any difference. Okay, does anybody remember the formula for the area of a trapezoid? Okay, I bet you will when I wrote it down. Okay, it's 1/2 base 1 plus base 2 times the height. And the height, maybe I should say it this way, the height is the distance of the pieces that are parallel. So this piece right here and this piece right here form the height. So the height is actually a height of 2. Okay, so the height is going to be the pieces that, this is almost like, looks like, we think of it maybe as being a trapezoid on its side, right? That's how we would probably picture this in our mind based on the trapezoids we've seen back before. So the height here is 2. The bases are the unequal length pieces that are parallel. So this piece right here on the y-axis, I almost get for free because I plotted the point there, right? The height along the y-axis is a height of 4, right? What is the height on the right-hand side at x equal to 2? 10. Yeah, sorry. I couldn't hear people very clearly. 10. It's a height of 10. So those are the two heights that I have. So what this is actually doing, just to remind you from geometry, is you're averaging the heights of the two bases. That's what you're really doing. So when we add 4 plus 10 and we divide by 2, the average height of my bases is what comes out of that. So this is 1/2 times 14 times 2, and what do we get for our area? What do we get? 14? Because these cancel kind of nicely on this one, right? So area is 14. If you think of this as a rectangle and a triangle, you can do that as well. So the rectangle piece is just the base times height. And I'll call it base 2 times height because there's 2 bases that I'm talking about. The triangle piece is 1/2 a base. We'll call it base 1 times height. And those would not necessarily have to be the same pieces, so we'll call them separately. So let's look at the triangle first. The triangle has a height and a base, and you can look at those. So what are the base and the height of my triangle, the top piece?
Base 2 height.
Base 2 height 6.
Oh.
Yeah. So the base is 2. The height is 6. So on my picture, here's my 6 and here's my 2. Now my rectangle at the bottom, what do I have?
4 and 2.
Yeah, so I have a base of 2 or a height of 2 either way, and the other one's 4. Those dimensions are 2 and 4. So I have 2 and 4 down here. Okay? And if we multiply these out, this piece gives me the 6 right here, plus, and this piece gives me 8, and 6 plus 8's 14. So you're welcome to do it from that perspective if you prefer. And neither one's better than the other. They're just different perspectives. Okay, so far so good? Okay, so there are 2 special definite integrals that we're going to take a look at next. One talks about what happens when you have an integral from a to a. Now, can you imagine over here in these pictures, if I started and stopped at 2? Area starts at 2, area stops at 2. What would the area be? 0. There's no width to be discussing, right? And so, in fact, when you have the limits of integration that are the same, you get 0. This rarely shows up, but it's at least worth noting that that's a strange case, okay? The second one actually talks about what happens when your limits of integration flip. So if I've got the limits of integration going from a to b, and I flip them, and I instead go from b to a, what happens is we actually reverse all of our signs. And so if I switch my limits of integration over here on the right-hand side, I'm going to get the negative or the opposite sign of the integral I should have been getting. You might be saying, well, why would we? Why would we do that? And it's going to show up here in just a moment, okay? So there is a reason for it to showing up, which is why we need to describe what's happening. All right, 4-6, additive interval property. Okay, so we mentioned before that if it's continuous, it's automatically integrable. But I also mentioned that there's some things that are not continuous that we can also still find integrals for. Well, we can do that because we can break it apart into pieces that do work, and here's how. So if f is integrable on 3 closed intervals determined by a, b, and c, then the integral from a to b of f of x is the same as the integral from a to c and from c to b if c is in between a and b. So imagine if you had something like this. This is an arbitrary picture, and you had the interval starting at a, it ends at b, and c is somewhere in between. And you had something. If you were finding the integral over the entire interval from a to b, clearly you could just find it from a to c and find it from c to b, and it should be the same thing. Right? That's not exactly what I did when I changed my trapezoid into a rectangle and a triangle, but it has the same sort of feel. If I take an area and I break it up into a couple of pieces and find those pieces separately, it should be the same thing as the area of the whole interval to begin with, right? Why is that valuable? Well, because like I said, this is being arbitrary. What if you had a graph that did this? And you wanted the area from A to B. Well, it's not continuous, so I don't for sure have the ability to just find it. Like there's no guarantee for that. But I should be able to find it because I should be able to find this area, and I should be able to find this area, and I should be able to add them together. And it would be the whole area, right? So that's what this allows us to do. It allows us to break things apart into pieces when I don't have continuous functions, usually is when this is used, that I could still find the areas for and add them together. One more property of definite integrals that we've seen this property show up not for integrals, but we've seen it show up in a variety of locations for limits, for derivatives, for antiderivatives in section 1, section 4.1, and they show up here again too. So if f and g are integrable and k is constant, and we actually have functions k times f and f plus or minus g, we actually have all the same properties that we've had anytime we've had these sort of things show up. And because the limits are happening behind the scenes, right? We saw them with Riemann sums as well in section 4.2. That's another place we saw it. So when I have a constant times my function, I can pull the constant in front and I can find the area, right? If I have two functions either added or subtracted together, I could separate them and do them individually and add or subtract their results. The reality is just everything that you want to be true, just like it was for limits and for the summations, it works. It all works for us. And that's really good news. Now, if you think about it, you might be saying, well, wasn't there one place when something didn't work the way we expected? And there was. It happened with products and quotients. Do you remember that? And you might be saying, well, what about those then? What about when we have products and quotients? And I'm going to tell you, you get to start on that when you get to Calc 2. That's where we start looking at what happens when things fall apart a little bit, when they don't work quite like what we would hope or expect them to work on. We're working on the precursor to that, which is where all the pieces do have these kind of components, because all we're looking at sums and differences and constant multipliers, not products and quotients. All good? What that means is when you see products and quotients, there must be some way to algebraically simplify them to turn them into one of these, right? So when you do see those, recognize, I can't leave it in product quotient form. Something has to be able to simplify with algebra that I know how to do. Okay, so let's take a look at what happens when we're using these two properties, actually the three properties, the last three pieces that we've looked at, on some functions. So taking a look, we will finish this section today. I won't change the homework though. The homework will still be due on Friday, okay? You good with that? You're like, no, let it be due on Wednesday, right? No, Friday, we'll keep it on Friday. So we will just do antiderivative gateway only on Wednesday. Okay, so the interesting thing about these materials right here is that we're going to find other ways to actually find them later. That's in section 4.4, which we'll start into on Friday. But what this section actually tells us, or this question actually tells us, is it tells us the three values that we're going to need. It tells us that the antiderivative from 2 to 4 of x cubed equals 60. And we haven't done that yet. We will. And you'll know how to do that on Friday. But right now, they're just telling you it does. So you're just taking it at face value and you're just going to go with it, okay? The second one is that the antiderivative of x from 2 to 4 is equal to 6. We could actually show that one right now with geometry. We couldn't do the x cubed one with geometry at the moment. That's not something from a geometric perspective that you have a formula for. But the x one you would. And the last one is that the antiderivative from 2 to 4 of just dx. Now, when you see something that just says dx, please know that means there's a 1 there. If there were a 0, we would have it's a constant, right? The antiderivative of a constant is 0. So if you see something that just says antiderivative 1 dx, it means that you've got a number 1 there. That is important to remember. So if this were our function, we could do this with geometry as well. It was like our y equal 4 one where we had the horizontal line, and we could actually find the area and it would be a rectangle. So we could do the last two pieces of this with geometric formulas if we wished. That's not what we're asked to do here. They're just giving us these pieces. Why? Well, because they're going to have us evaluate a couple of pieces using them. So you see that we've got the antiderivative from 2 to 4 of x cubed minus 3x plus 8. I know there's a script x. I know that you know how to take antiderivatives because we've did section 4.1. That's not what this question is asking. This question is asking us to utilize the properties that were just introduced. In particular, I can separate out each of these pieces because it's addition and subtraction. So this is the first piece. Remember bookends. Make sure if you start the integral, you put it the dx at the end. The next piece has a subtraction and there's a 3. Now notice, this does not have a 3 in it up here. So I'm going to drag the 3 in front of the antiderivative. That's the property that we saw over here on number 1. It says if there's a k inside, I can pull the k to the outside. So I'm going to do that. And I might as well pull the negative with it. So the negative 3 will come to the outside, and it's the x. Still from 2 to 4, still bookended with dx. The last one is an 8. Again, I don't have an 8. I have a 1 up here. But 8 times 1 is 8, right? So I can pull the 8 out as well. And it leaves us here with a 1, or you can just leave it off entirely if you wish, going from 2 to 4. You have to show this step. This step is what allows you to now use the pieces of information that they defined for you. So it's very nice, it's very friendly, because what this actually says is, well, I know what the antiderivative of x cubed from 2 to 4 is. It's 60, and I can actually take that down here, and I can replace this with the number 60. It's just 60 minus. And then I have a 3. And I can do the same thing with the next piece. We'll use blue. The antiderivative from 2 to 4 of x dx is 6. So I have a 6 right here. And then the last one, antiderivative of 1 from 2 to 4 is 2. So I have my plus my 8 on the outside, and then I have a 2, and it's arithmetic. Right? Adding, subtracting, multiplying, dividing, potentially. So we're going to just add these pieces and so forth straight across. So if you do 60 minus 18 plus, what do we have? 16, what do you get? 58. Okay. Are we good? Okay, we have one more. How is this one different than the last one? There's a couple of things, one in particular. Yeah, the A and the B are flipped. That's what Brock just mentioned, right? So they're flipped. Well, we had a property that said what to do when they were flipped. What did it say over here that I need to do? Did I pass it? I did. Where was it? There it was. It said change all the signs. So I'm going to flip it, and I'm going to change the signs. In particular, I wanted to flip it into something I use or have, right? What I have is the integral from 2 to 4, and I can make the negative in front. If you wish to move the negative through, you can. So if you would like right now to make that negative x and positive 7, that's fine. If you want to leave the negative at the end and just do it outside after all of it's done, you can do that too. I'm going to leave mine on the outside. I still need to separate these just like I did on the last problem. So the x is right here, bookended with dx. And if you wish, you can put the brackets here, and then I can pull the negative 7 out, just like I did with the 8 on the last one, like this. Or if you want to distribute this negative through and make this integral negative and this one positive, you could do that. Doesn't matter. So take your pick. I'll just leave the negative at the beginning. So what is the antiderivative of, I used blue, we'll use blue again, of the x dx piece? Well, it's 6. So I have a negative, and I have a 6 here, minus 7. And then my antiderivative of the 1 dx is 2. So I have 7 times 2. So 7 times 2 is 14. 6 minus 14 would be 8, but negative, right? And then the negative at the beginning would make it positive. So this should give me a positive 8 after the arithmetic takes effect. Okay, Gateway Wednesday is your priority to prepare for because this assignment is not due until Friday. But if you would like to start it, you certainly could.